All right, control hazards. How can we handle pipeline branches and jump instructions? Well, this turns out to be a bit of a problem because we send the target to the PC if the test is equal back in memory, which means that these instructions are not correct. So for example, we do compare 1 to 1, which would be equal, we jump to 10. We would actually start reading subtract and then realize over here, oh wait, we don't mean to execute subtraction. Oops, what do we do here? Well, we could avoid it, make sure there's no hazards in the code. That'll be interesting. We could detect install every time we fetch a branch or a jump address. We wait until it resolves before going forward. Excuse me. And the last thing we could do is speculate it and then just squash everything if we end up being wrong. So how do we avoid it? We don't have any branch instructions. Well, that turns out to not be practical because that means we'd have to write programs with no if statements, no while statements, no looping structures of any kind. Yeah, that'd be bad. Another thing we could try and do is called a delay branch, where we do delay EQ, and basically programs or instructions at PC plus 1 plus 2 will execute before deciding whether to fetch the PC plus 1 plus offset. If no useful instructions can be placed after DB, the delayed branch, no ops must be inserted. Well, now we're back to our old programs no longer operate because we have to recompile all the code so people don't want to buy your processor. You now have a bunch of no ops in your code, like the Intel Epic had 25-40% extra no ops. And your CPI does technically equal 1, but that's cheating because a lot of your code is no ops. So in other words, the avoid the problem is a terrible solution. Detect install. So once you find the opcode and it's to a JA, and we didn't do jump and link, but that's another type of linking one, and I'll leave that there for next time I teach this course. Keep the instruction fetch and pass no op to decode, aka don't execute it until we finally get there. So in other words, once you detect a jump, you just put in no ops here until this thing finally resolves, and then you're done. So for example, the subtraction, you jump. Once it's in fetch, you fetch subtraction, and then once write back happens, you either fetch from subtraction or where the target is, and you fetch that one instead. Okay, that does work. CPI increases every time a branch is taken. Is that necessary? Not always. Only about half the time the branch is taken. Think about this for a moment. Only half the time the branch is taken. Only half the time the branch is not taken. So if we just predict that it's taken or not taken, then we're at least correct 50% of the time. And then we can ignore, we'll just treat what's nice is if we predict not taken, then we just treat it as a no-op. And then if we're wrong, then we go back and we squash all the instructions and fix it. So this is called speculating squash. So assume not equal, keep fetching, and then squash if things are wrong. So for example, if we go over here, we find out that they are equal, and we need to update the program plus 1, we just throw no ops to these guys. And this is fine because the state of our register file isn't updated until write back, so just squashing these and turning them into no ops is all we actually need to do. So CPI increases every time a branch is taken, which is about half the time. Is that necessary? Again, no. But how can we fetch from the target before you know the previous instruction is a branch, much less whether it is taken? Well, you can't, but you can always predict, aka if a branch was taken, you say, hey look, this branch was taken right here, let's store the target. If these two are equal, load from the target instead of from program counter and move on. AKA, if the last time you were at this branch it was taken, go ahead and take it again. Alright. Well, now we need to predict when something's taken. Because notice in this structure, I'm just loading one branch PC and one target. This could be a very large structure storing multiple entries. But now we need to predict, in this situation, we just said last time it was taken, go ahead and take the instruction. Go ahead and take the branch. Can we always do that? Well, turns out to be a little different. If we predict not taken, we're accurate 50% of the time. If we predict backwards taken, 65%. What backwards taken means is that if the offset is negative, predict taken. Now, why would this be more accurate? Well, most of the time you're in a loop, and a loop always goes backwards. So this is capturing the majority of loops, except for that final iteration where you have to jump out of the loops. Predict the same as last time. This requires this goes up to 80%. You might be thinking, well, why don't we just stick with this? The problem is same as last time. You have to keep track of the history of all your previous branches. This one, your prediction's based on the offset, which is nice because that means all the data is already encoded. You don't have to add another structure. But here you have to have a history table, and that's about 80%. Think about this. Now we're just 80% accurate by just keeping the history. The old Pentium, 85%. The Pentium Pro, which was a huge leap, 92%. And a lot of paper designs are at 97. I think a lot of our processors are around 94, 95, which is crazy high accuracy. And we're not going to get into all that. We're just going to talk a little bit about branch prediction. Alright, so execution time, number of instructions, times cycles per instruction, times cycle time. Multi-cycle decreases cycle time but increases CPI, because remember, in a multi-cycle, which is previous to pipeline, we chopped up the instruction into multiple cycles. That decreases cycle time, which means that we can increase our clock rate, but increase CPI because you have to wait for every instruction to complete. Pipelining decreases CPI on top of multi-cycle back down to 1.0 if no stalls. Hazards are hopefully fixed by stalling, and you get the advantage of decreasing cycle time, and that's how pipelining increased performance. So, calculating performance, no stalls. How many cycles does it take to execute if there are no stalls in here? Well, this starts at 1, this starts at 2, this starts at 3, and so it'd be done at 7. Great. What values are written to the ALU result field of the memory write-back pipeline register at the end of cycle 5? Well, cycle 5 is when this guy's over here, so he'd be forwarding his value along. How many data hazards are in this code? 3. Well, let's see how many there are. This 3 requires on that one, and this 3 also requires on that one, so that's 2 that this one is causing, and of course this 5 requires this one, so that's a third. How many stall cycles if we use detect and stall? Well, you have to stall twice over here, and once you do that stall, notice that this hazard also goes away, so you don't need to worry about that. And then you need 2 more after this one, so you have a total of 4. Where did the values for the and instruction come from? It comes from, the previous add, so you have to get this result right there. What is the CPI of the code on the LC64 data path with data forwarding from lecture? It's 2 because it hasn't, you have 5 cycles or 5 instructions. It takes, we'll just say 10 in order to complete, so the CPI is 2. If this became 20, it'd be something like 1.5 or something. Alright. So, detect and install, calculating performance, read the code with branches. We don't have the code. Okay, great. Alright, I'm just giving you examples of what problems you may encounter. How many cycles are saved if you perform speculate and squash, assuming not taken? Well, since at this point you would stall 3 cycles, you're actually saving 3 because you don't have to put no ops, you're just guessing that it's not taken, and then you move on. Classic performance problems, so you have move load 10%, move storeward 15%, jump is 25, R-type is 50, speculate always taken, and squash. 50% of branches taken, so that means 80% of these branches, so 80% of 25% do not cause any problems, but that last 20% does cause a increase in 3 cycles. Full forwarding execute state, 20% of lows stall for 1 cycle. What's the CPI of this program? Classic performance problem. I wish we had a board. Okay, now we've talked about that. Those are the things that you're really going to be tested over. I do want to go over a couple more features because these are going to end up being very important for security purposes, and there are a lot of reasons, and this will lead to how Spectre and Meltdown occurred. So exceptions are events other than branches and jumps that change the flow. For example, you hitting a key on the keyboard, a timer says, hey, look, the timer's gone off, received network data, an exception happens. So the question is, how do we deal with them? And what do we do? Well, or for example, the ALU overflowed, or you divide it by 0. You can flush the pipeline after the exception or handle the exception. The idea is once the exception happens, you flush everything previous, you put some bit codes in a bit field saying that, hey, look, this exception happened, and then you execute what's called the exception handler. So we haven't gotten into operating systems yet, but every time you run a program, the operating system is keeping a data value for when for where you need to go when an exception occurs. And this in general is the operating system. And so it will, once an exception happens, the processor knows where to jump, aka the OS, the kernel, and goes there in order to handle the exception. It does end up being harder with pipeline because multiple instructions execute at the same time. You might have false exceptions are also possible. So you have to flush all the ones, but there are false exceptions. For example, the exception may occur at different points. Let's get to an example here, please. There we go. Whew. So if you're doing a division, 10 divided by 0, that's going to happen in the ALU. If you have a bad opcode, that's going to happen in decode. And in our previous cycle, those happen at the same time. So which one do you actually report? Because you got both of these happening, and they can happen at different points in the pipeline, aka they could happen in memory or they could happen earlier. Well, generally you give priority, and you give priority to the early instruction over the later instruction. And so hopefully the divide would cause the exception and not the bad op. This unfortunately is going to get even more problematic in a moment. Oops, wrong button. But before we go into the other issues, let me talk about a couple other processor designs on top of this 5-stage in order. We're not going to go into too much detail, but do keep this in mind because it'll be very important for Meltdown Inspector. So anything that has more than 5 stages is called super pipeline, which enables the clock frequency to be increased even more because you've chopped up all the stages in different cycles. Of course, super pipelining just makes the problem of data forwarding even worse because now you have more stages that you have to forward data. And what happens is, and you'll find this out in the processors, is we did go up to 35 stages, but we've tailored it back to 20 as the optimal amount in order to capture pipelining. So most processors, or modern high-performance processors, are super pipelined to about 20 stages. Now a superscalar machine is going to be different. So super pipelining was increasing the number of stages. Superscalar is when you have multiple execution paths along your processor. So you'll be able to fetch multiple instructions and you'll have multiple pipelines inside of your processor. And then you've got to handle the idea of being able to execute 2 different instructions at the same time. And that's called superscalar. We're not going to talk about scheduling right now. That's a little too much. The last thing we do want to talk about is something called out of order, and this is a very important feature, especially for a Meltdown Inspector. So we've talked about the 5-stage in order pipeline. There is the out of order execution, and this is an advanced architecture topic, but let's at least briefly talk about it because for Pipeline Inspector, the idea is that you'll have your instructions, and if there's a stall between certain instructions that you may detect, you're going to go ahead and go forward and try and find another instruction that you can go ahead and execute. So this is called out of order execution because you've taken the instructions and you're executing them not in the order that they're written. Another example might be that when a multiply might take 10 or 20 instructions, while that's happening, you might as well try and complete the add instruction that's coming up, or an and or whatnot, as long as there's no hazards. So this actually tries to look down the pipeline and look into it. Let's see if we can take a good picture. There we go. So in fetch decode, I'm going to just call it some magic in order to help things out. If you take advanced, this will make sense. But notice that it then executes into memory or execute stage, and there can be multiple execute stages that it can go through, and then eventually it's sent back to what's called a reorder buffer in order to serialize the instructions and then commit them in order. So the idea is that it basically takes the instructions, sets it up, throws it out into a field, and then when it's done, it goes ahead and commit it. So this is the idea of out of order execution, and this actually allows instructions to be executing out of order so that the processor can look into further down your code to find other instructions in order to execute while its current instruction may be taking a while to complete. All right, so a lot of that is a little confusing. We're not going to go fully into the Pentium Pro architecture. That's beyond the scope of this class. But as I've mentioned before, the IA32 or 32-bit instruction set is very complicated indeed. And I think we already did that in assembly, so we don't need to go over it again. All right, that's all for the discussion today.